Hello, this is Mr. White, and this video is about using function transformations to write a Batman equation. August 29th, 2012, 7-year anniversary of Katrina, Isaac barreling down outside, the power out, the wind howling, and in the Gulf Coast spirit of not letting such things stop us from doing what we do, it's only by the power of a laptop battery that your nerdy math teacher is putting this lesson together. And I'm excited because I've been wanting to do this lesson for a long time. It starts with a former student of mine named Rebecca. Rebecca is now up at college in Maine, and she sent me about a year ago an email asking if I had heard of the Batman equation, and I had not heard of it at that time. So Rebecca shared it with me, and she asked, why didn't we ever do anything this cool back in pre-calculus? Touche, Rebecca. Now we're going to do something this cool. This Batman equation, if you just Google Batman equation, you'll find plenty of links and information on it. And the idea is that somebody came up with a single equation, purportedly, that if graphed would produce the Batman symbol that you see before you here. And a lot of people on the internet didn't really know what to do, how to deal with the mathematics of the equation. They were asking, is this real? Does this really work? Well, the short answer is yes, it does work. I think the more complete answer would be to say that it works. It's really about 6 equations, which are very clever, but it's really more like 6 equations cleverly manipulated to look like they're one equation. But nonetheless, it was a very cool thing, and I thank Rebecca for sending it to me. I kind of got on this kick where I tried to come up with my own graphical equations here. And some of the ones I came up with my own version of a Batman symbol that was simpler than the original Batman equation. And then I came up with the Superman symbol and a better Superman symbol, and then my own symbol, my own little logo, a Saints logo, a thumbs up. And again, you're seeing all the equations here too. And don't be intimidated by these equations. What we're going to do in this lesson is not as nasty as what I was nerding out on here. This is called the Penrose triangle. Math dude, math dudette. And again, these are all drawn on my TI-84 by entering function equations. A cat, a dog. So how do you even go about starting something like this? Well, you thankfully have the knowledge. You know about function equations, and so you might be surprised how much you're able to do. This is what we're going to develop in this lesson. A simpler, what I'll call a baby bat. And before we actually jump in, hopefully you are looking at that and saying, yeah, I see the parabolas and the absolute value shapes and the line segments. Hopefully you have some sense of how we're going to tackle this. But before we do that, we need to learn how to restrict the domain of the functions in our calculator. And what I mean by that, if it's not clear, is to just recognize that I don't want all of these graphs. So for example, this parabola right here that I'm tracing out, I don't want all the parabola. I don't want it stretching all the way from here to here, having a domain from negative infinity to infinity. I just want part of the parabola, just this part. And same with every other curve. So the bad news is our calculator does not have a built-in functionality for intended for restricting the domain, but the good news is it does have a functionality that can be used as a clever workaround. So let me show that to you. Now maybe you start by entering this into your calculator. 9 is less than or equal to 7. And your first question is, Mr. White, how do I get that less than or equals to into my calculator? And I shall show you. So type 9 is less than or equal to 7. You type 9, of course. Whoops. Calculator's just taking a little time to catch up with me. There we go, 9. And then go to second. Hit the math button to get the test menu up above it. So second, math, to get the test menu. And then you see that item number 6 here in this list is less than or equal to. So I could arrow down, but it's quicker to just type the number 6. So second, math, 6 is how I got the less than or equal to button. Keep that in mind because you're going to be using that quite a bit in this lesson. So then you just, of course, type the number 7, hit the enter button, and see what happens. I'm not going to display it right now, but see what happens on your own calculator. As always, I want you actively listening and following along. After you've done that, and you're probably wondering, why did the calculator give me that? Well, keep playing with it. Why don't you type 3 less than or equal to 7 and see what the calculator gives you. Type a few more, make up your own, play around with this and see if you can figure out what's going on. Try this. 3 is less than or equal to 7 and 7 is less than or equal to 9. Let me show you where to get that and. Oops, that's not what I meant to get. Here is the calculator again. So if I want to get and, I will again go to second and then the test menu right above the math button. But this time I'll arrow over to this logic menu, and there's my and. And then I could type, the second inequality after this, hit enter, see what happens. And finally this one. So if you've done all this correctly, and again, I hope you've played around with it a little on your own and come to your own conclusion on what it's doing. But your calculator has been outputting 0, 1, 1, and 0 in these cases. And if you haven't figured it out already, those correspond to true and false outputs. In computer programming, very often zeros and ones represent true and false. The fancy name for this are Boolean operators, if you want to look that up. Or if you just want to remember 0 is false and 1 represents true in this kind of scenario, that's good enough as well for this lesson. Okay, so we're going to take advantage of this calculator functionality, which is typically used, as far as I can tell, in making programs for the calculator, but we're going to use it to restrict our domain. And let me show you how that works. Go ahead and enter this into your calculator, please, and graph it going to zoom standard, zoom number 6. Zoom standard on your TI-83 or 84. On your TI-84, remember to use the alpha F1 to get this nice horizontal fraction bar and enter it exactly as you see here. TI-83 users, you'll have to enter a couple pairs of parentheses to make that work, but should work the same other than that. And what you should see before you, I'm not going to do it up here on the screen, you should be able to see it on your own calculator, is you should see the graph y equals x plus 1, but its domain has been restricted to, for only x values between 2 and 7 inclusive. So this gives you a sense of how we're going to restrict the domain on our calculator. So let's jump into the baby bat equation. There's our baby bat. I'm going to label each piece of the baby bat as you see here on the screen. Make sure you notice in particular that for Y8 represents both of these line segments. Those are not two separate equations. And Y9 likewise represents both of these line segments. So total of 9 pieces to make this baby bat. We'll do 3 of them here together, and I'll ask you to do the other 6 on your own just to make sure you're getting the hang of this. Let me ask you right from the beginning, please set your window settings as such. Your X-min and your X-max would be -10 and 10 respectively, and make your Y-min and your Y-max -7 and 7 respectively. All right, let's jump in and let's figure out how do we do Y2. Now, you should know how to do that by just looking at the endpoints, the coordinates of the endpoints, and doing your old y equals mx plus b. But I'm going to ask you to look at this in a different way, and there's a purpose to looking at it in this different way. I want you to look at it in terms of transformations. Think of the basic function y equals x, which is a line that goes through the origin and has a slope of 1, right? I'm going to just draw a piece of that line, and I think you'll figure out why if it's not already clear. I'm going to just draw a piece of that line segment and then ask myself, what do I need to do to transform that red line segment so that it looks like the blue line segment? Now the order, you may look at it and think of transforming it in a different order than I choose. You have a little bit of flexibility in what order you do it in. That's something I'm sure we'll be working through in class. But I'm going to say first thing I want to do is I want to reflect it across the y-axis. So if I reflect it across the vertical y-axis, it would look like this, right? And then I'm going to say I want to move this 3 units to the right. 1, 2, 3. And 2 units up. 1, 2. And already it's looking pretty close here. I can tell I just have one more thing to do. And that is to vertically stretch it. Right now, this red graph goes to the left 1 and up 1 unit. But what I want it to do is go to the left 1 and up 1, 2, 3, 4. So I want this height to be 4 times as tall as it currently is. And so that means I need to vertically stretch it by 4. So imagine grabbing the top and bottom of that graph and stretching it up vertically, making it taller. And there, I've accomplished what I set out to do. These are the transformations that I just described: a reflection, a translation to the right, a translation up, and then a vertical stretch. And notice that the domain is from 2 to 3. Hopefully you're comfortable enough with that concept now. I'll just draw it real quickly on the board here. The domain is all the x values between 2 and 3. So let's go ahead and apply these transformations to the basic function. The basic function was y equals x. First thing I wanted to do was reflect it across the y-axis, and we do that by putting replacing the x with a negative x in parentheses. I could put the parentheses here. In this case, it clearly doesn't make any difference, so I won't. But the general rule is to replace x with parentheses negative x, and that's how you reflect across the y-axis. If I want to translate it 3 to the right, here's where you got to be careful. Remember, the rule is to erase the x and replace it with parentheses x minus 3. This is the counterintuitive one. We might intuitively think it's x plus 3, but we have to remind ourselves that since this is horizontal, it's counterintuitive. If I want to translate this 2 up, I put a plus 2 on at the end. That one is intuitive. And finally, in order to vertically stretch this by a factor of 4, I insert the 4 in here outside the parentheses. And I went through that a little bit quickly, but hopefully you've done enough in class where you can look at that and say, yeah, that makes sense. And that is the linear equation for the line segment we wanted. Now, to make it look a little more familiar to you, personally, I don't mind just writing it just like this, but I think most students are most comfortable with doing this. I'll go ahead and label this y2. That's really what we're dealing with. I go ahead and distribute that, negative 4x. Remember to distribute the negative sign. That's plus 12 plus 2. And of course, a 12 and a 2 combine to give us a 14. That is our linear equation. That is the same equation you would have gotten if you had just set out the old familiar, set out to do the old familiar mx plus b method. So this is the equation, and notice that I have entered in the domain underneath. The x's between 2 and 3 inclusive. That's what I'll ask you to go ahead and type in now in your calculator, and go ahead and put it in the y2 slot, and you should see the segment that we were trying to create. All right, for our next one, I'm going to do this one a little bit more quickly. Hopefully you're getting the hang of it. But let's do y6 next, and we can see that that is definitely a parabola. Here is our basic parabola going through the origin and the points 1, 1, and negative 1, 1. And again, the first thing I want to do here is flip it, but this time I want to flip it across or reflect it across the x-axis. So would look like this, right? And again, speeding it up a little bit, I will move it to the right 6 and down 2. Here's where I'll slow it down a little bit. I hope those were clear. But this next vertical or horizontal stretch or shrink is where I could see some students getting a little bit confused. So let me move this picture up a little bit. I knew I had a little extension to my graph there, planted there. This is where I'm at so far after the reflection and the translation right and the translation down. And now I'm asking myself, how do I stretch or shrink this? Well, I would suggest that you look at it this way. On the original graph, or I'm sorry, on our red parabola here, I am currently going over 1, 2, 3, and down 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a height of 9 if I am focusing on this point right here. What I would like it to have is a height of 2. I want to go over the same 1, 2, 3 units, but rather than a height of 9, I want it to go down 2 units. So if it's currently 9 and I want it to be 2, that means I need to vertically shrink it by a factor of 2/9. So let me go ahead and summarize here, and the step I was just describing here, vertically shrink by a factor of 2/9. That should make it smaller by a factor, height-wise, by a factor of 2/9. Okay, so let's again go ahead and apply those transformations to the basic function. I'll start with y equals x squared. And if the first thing I want to do is reflect it across the x-axis, remember we do that by just having a negative sign outside of the function. So that is not a negative x inside parentheses squared. If I wanted parentheses, it would look like this. But I'm going to go ahead and do without, because I don't have to have them in this case. And that's our reflection across the x-axis. If I want to translate it 6 units to the right, hopefully you're already ahead of me on that one, I'll erase the x and put x minus 6 in parentheses, emphasizing those parentheses here. That's 6 units to the right. If I want to do 2 units down, that's at the end a minus 2. And finally, if I want to vertically shrink this by a factor of 2/9, oops, smartboards, I think was trying to outsmart me here, and maybe it did, I don't know. Oh, goodness, that's terrible, making me look bad. But I'm going to do this all in one take. I'm not going to edit that out. Despite what students may want to believe about me, I am slightly short of perfect. That's a joke. Okay, I think I got it here. Vertically shrink by a factor of 2/9. That means putting a 2/9 here. That's our vertical shrink. And again, if I look at the picture, I can see that the domain, I really only want the x values between 3 and 9. I'll bring this down. I'll use between 3 and 9. And so the way that I would do that in my calculator is type it in so that it looks like this. If that didn't make sense, if you need to hear it again, please pause and replay. If it made sense, go ahead and type that into your Y6 slot on your calculator, please. All right, let's move on. Let's do one more together before I have you finish up the rest. And this one I'm really going to speed it up, and rather than do it so much step by step, I'm going to go ahead and just ask that you pause and think about what transformations of the basic function absolute value of x, which looks like this. You pause for a minute and think about how that needs to be transformed. And then when you press play again, you can see if it agrees with my answer. I'm going to go ahead and bring my transformations out here. I'm going to say that we want to reflect it across the x-axis, translate it 2 to the right, 2 down, and then vertically stretch it by a factor of 2. If you have an answer that's different than mine, don't automatically assume that you're wrong. Your answer might be correct as well, and I would encourage you to try to apply your transformations and type it in your calculator and see if it works. When I type my transformations in there, it gives me this equation, or when I apply my transformation, it gives me this equation on the domain from 0 to 3. And again, I hope you'll pause and make sure that it's clear what each one of those numbers does, what transformation it represents. So enter that in for y8, and then go ahead and do the rest on your own, please. Again, the ones that we've done together here are y2, y6, and y8. And go ahead and do all the remaining 6 equations on your own. And if you, it's going to take you a while, I'll admit, but if you can tackle this, if this makes sense, I think you're really in great shape for the next class. Let me remind TI-83 users, or let me go ahead and comment that for TI-83 users, I could imagine that the parentheses can be a little bit overwhelming in this exercise. If they are overwhelming you and it's getting to the point where you feel like you're about to give up, rather than give up, don't worry about the restricting the domain. Just at least get the equations right, at least get the transformations, and then come work with me during office hours, and I'll help you work through the domain issues. The effects of that, if you just type in the functions without restricting the domain, again, as discussed before, you can imagine that these, for example, this parabola y6 will continue to go on forever, and this other parabola y4 will continue to go on. It'll look awfully messy on your calculator, but hopefully you'd still at least be able to make out the Batman symbol through all of that. All right, again, this is where you pause, do the rest on your own, because in just a second here, I'm going to go ahead and go on to my equations. Here are the equations that I came up with. And as far as restricting the domain goes, I'm going to reveal those right now. Those fraction bars with the restricted domain underneath, if you enter those into your calculator, you should get your baby bat. Let me go ahead and make a couple closing remarks. I know this video is going long, and I thank you for staying tuned. But I can't resist. I feel this is something you will want to know. You notice that some of those shapes were reflections of other shapes. So for example, y2 and y3 were just reflections across the y-axis. There is a shortcut for entering that in your calculator. I intentionally did not tell you that earlier, but I'll go ahead and reveal it to you now. And you can see it in the equations. The equations certainly have a lot of similarity to them. And you could type it in just the way you see it here on the screen, or alternatively, you could also do this. y3 equals y2 of negative x. And I'll ask you to think about why that makes sense to make y3 a reflection of y2. The way we would type that into our calculator, on your TI-84, you'd go to alpha F4, which is right above the trace button. On your TI-83, you'd go to vars, y vars, and then hit enter when it prompts you or when it says function. So if that didn't make sense, if you didn't follow that, I'll ask that you please ask for clarification in class or during office hours. Hopefully you see the other functions out there as well that are reflections of each other. y5 and y4 are reflections of each other. Likewise, y7 is a reflection of y6, y9 is a reflection of y8. And again, you can type those in instead of the full equations for y7, y9, and so on. So the very last point I'll make before I stop talking, I want to make this clear that what we've been typing into our calculator looks kind of like this, with this fraction bar. If you write that on a test paper, I'm not going to mark it wrong because I'll understand where the confusion came from, but I should be clear, that's not technically how we should write it on paper. So that's only how we type it in the calculator. On paper, we should write it like this. Write the equation, then on a separate line, say that the domain, or as you probably see me abbreviate it in class, just write d colon and then -2 to 2. And you should be comfortable with our interval notation as well. So the very last note I'll make, and then I promise I'll stop this video, is that you may program all this in your calculator. You've just spent a considerable amount of time entering all these equations in, and if you're a little bit upset at having to lose all that work, you can enter all these equations in the form of a program on your calculator, and if you're interested in doing that, ask me about it in class, ask me about it during office hours. I'll be glad to show you. And within a few minutes, if you're willing to play around somewhat on your own, I think I can get you started in a couple minutes, and you can probably take it from there. All right, thank you for your attention. I hope this has been clear and has helped you understand function transformations.